Today is going to serve as an introduction to op-amp circuits. So I'm about to tab over to a screen to show you guys a circuit that you do not in any way, shape, or form need to draw or anything like that, because I'm going to be very explicit in saying we are never going to analyze anything like that in this class. And realistically, the electrical engineering students are never going to analyze anything like it until they're seniors and they take a specific course on integrated circuit design. Okay. So this big terrifying circuit here is a simplified version of the internal workings of a Texas Instruments MU-A741 operational amplifier. Okay. So we can see a few different things here. First, this giant ugly circuit contains a whole bunch of bipolar junction transistors, 22 of them to be precise. There are 11 resistors. There is a single diode, and there is one capacitor in this simplified view of this circuit. So to this point in this class, we have not talked about transistors at all, although you guys, I believe, talked about MOSFET transistors very briefly during the Engineering 120 series. Additionally, there is a diode in this circuit, and I know that you guys talked about LEDs. You probably had a flyback diode. Or actually, you may not have had flyback diodes because you guys don't do the fish tank anymore. I don't know. But you may have had some limited experience with diodes as well. Transistors and diodes are nonlinear circuit elements because the current and voltage flowing through them are not proportional to each other. For BJTs and diodes, there's an exponential relationship between current and voltage, which is inherently nonlinear. And for MOSFET transistors, the relationship between current and voltage is dependent on the voltage squared, again, a nonlinear operation. So how are we going to analyze this big nonlinear circuit thing in a class that is specifically focused on the analysis of linear circuits? Well, we are going to be using what are called the ideal op-amp rules today. And it's going to allow us to treat this big giant thing as kind of a black box that we don't really care what's inside it. We just know what the relationship between the different terminals are going to be. Okay. And like I said, later on for you electrical engineers, we'll go into much greater detail about where some of these details come from. But for circuits one, we are going to kind of gloss over a lot of things. One other thing that I want to point out, how many terminals does this device have? I count 7. In minus, in plus, offset N1, offset N2, VCC plus, VCC minus, and out. 7 terminals. Okay. Most packages don't come with 7 terminals. They come with 8. So one of these terminals will likely be dead. Like it's literally just not connected to anything on your 8-pin chip. The op amps that we're going to use in the lab Friday actually don't contain offset terminals at all, and there's actually 2 op amps on the chip. But there's a lot of different configurations and stuff like that. So in order to understand where you would connect things practically using an op amp, you need to have a copy of a data sheet with a pin diagram that tells you where things are, because they are not remotely consistent between various models. Okay, so, all right. So we have this big, ugly, terrifying thing. For our intents and purposes, we are going to represent an op amp using the following schematic symbol. Okay. A triangle, which is the generic form of an amplifier. Okay. So an op amp is what's called a differential amplifier, meaning that it takes 2 input voltages and gives 1 output voltage. So we are going to have 1 input terminal labeled by a positive sign And this is what's called the non-inverting input. We'll talk a bit more about what that name means here shortly. The input terminal with a negative sign is the inverting input. And then over here on the right-hand side, we will have our output terminal. For the intents and purposes of this class, these are the three terminals that we are going to be dealing with, okay? Now, I am going to draw the other terminals on here, but they are going to, I'm going to call them optional, but that's not entirely true, okay? So the first of the quote unquote optional pins that I'm going to put on is the VCC plus pin. And then down here, I'm going to put the VCC minus pin. So while these pins won't influence our circuit analysis literally at all, they are critically important because an operational amplifier is our first component that is an active component, meaning that it requires external power for it to work. So a resistor exhibits resistance regardless whether or not it's plugged into a circuit. A capacitor exhibits capacitance regardless of whether it's in a circuit, etc. An op-amp will not function if we do not supply external power to it. And typically speaking, we are going to apply a positive voltage to the VCC plus pins and a negative voltage to the VCC minus pin. Two other pins that were on the data sheet were null 1 and null 2. The op amps that we are going to use in our practical experiment on Friday do not contain these pins, but I want to talk to you a little bit about what they're for. So, do any of you know anything about microfabrication processes? Probably not a whole heck of a lot at this point. Okay. So microfabrication processes is all about the ability to line up masks with the various layers of your chip. And sometimes those masks get slightly misaligned, resulting in manufacturing defects in the chip that you're trying to produce. So one of the ways that these defects can, or one of the consequences of these defects would be that your output voltage of your op amp might not be 0 if you applied the same voltage between your inverting input terminal and your non-inverting input terminal, right? So if you had the exact same voltage connected to those two terminals, the expectation should be, based on how one of these things work, that your output voltage is 0. If it's manufactured poorly, it won't be 0, and those offset pins are used to literally just recenter that output at 0. That's all those pins are used for. We are not going to see them, like I said, in this class at all, and unless you're doing some sort of high precision amplification, so like biomedical engineering students might be trying to amplify a very small signal from a sensor that's measuring brain function or something like that. Unless you're doing something that's highly sensitive, the offset null pins really don't play any role whatsoever. It's just when you're doing high precision measurements that you would ever need to use them. I just wanted to mention them because they're on the diagram. All right, so these are the various pins of our op amp itself. Now I want to introduce the two ideal op amp rules. Okay. And I'm explicitly stating here that these are applicable only for negative feedback circuits. Every circuit that we are going to analyze in this class is a negative feedback circuit. I can talk briefly about what that means if you want me to, but because everything we're doing is this, it's not particularly necessary. Anybody want me to explain what negative feedback means, or are we good to go? Okay, so let me come down here on the bottom. If I have just an op amp like this, where I have some voltage, let's call it V plus applied here, some voltage V minus applied here, and some voltage V out measured here, this would be considered an open loop system because there is no feedback loop applied to the circuit. Okay, so it's literally just you putting the op amp in, putting voltages on the input, measuring the output, calling it a day. Op amps are very rarely used like this. Much more often, there is a feedback loop in place. So a feedback loop simply means that we connect one of our input terminals to our output terminal. So if we were to connect our non-inverting input terminal to our output terminal, this would be a positive feedback circuit, okay? And realistically, we would probably put some sort of resistance between the non-inverting input terminal and the output terminal. It doesn't necessarily have to be a resistance. It can literally just be a wire, but for biasing purpose and all that kind of good stuff, it will very likely be a resistor. So when we connect the non-inverting input terminal to the output terminal, we have positive feedback. If we connect the inverting input terminal to the output terminal, we have negative feedback. So all of our circuits are going to have some feedback path from the inverting input terminal to our output terminal, usually in the form of a resistor, but sometimes it could be a capacitor or inductor, depending on what type of mathematical operation we're trying to get our operational amplifier to do for us, right? So an operational amplifier is called an operational amplifier because it is a circuit that does mathematical operations on continuous time input signals, right? So by the end of Friday's lecture, we're going to see how op amps can be used to add add signals together, so voltage signals particularly, take the difference of voltage signals, scale voltage signals, invert voltage signals, meaning just change their polarity or multiplying it by a factor of -1. We're also going to see how they can be used to integrate and differentiate signals as well. So for instance, if you had a square wave and you wanted to make a triangular wave, you would use an integrator because the integral of a rectangular pulse would be a triangular pulse, etc. So, all right. So our rules for negative feedback op amp circuits are as follows. Number one, no current can flow into or out of the input terminals of an ideal op amp. So that means that this current is always going to be 0 amps, and the current shown below is also always going to be 0 amps. Now, This isn't true for a practical operational amplifier. A real operational amplifier has an input resistance on the order of mega ohms, okay? So the MU-A741 op amp that I showed you guys earlier, the input resistance is listed on the data sheet, but it's 2 mega ohms. Okay? Most op amps that are based on bipolar junction transistor technology have an input resistance on the scale of mega ohms of resistance. We bias these op amps using resistors that are in the kilo ohm region, such that the internal resistance of the op amp is much, much greater than the resistance of our network that we're connecting to it, so that we can ensure almost no current flows into the input terminals, making this rule effectively true. Okay. It wouldn't be true if we biased things with a mega ohm scale resistor, but we don't do that specifically because we want it to behave in this nice, neat way. Okay. For a operational amplifier that is based on MOSFET technology, the input resistance is usually on the order of tera ohms or 10 to the 12 ohms. So it's even higher, okay? So even in our worst case scenarios, if we are biasing our op amp circuits using kilo ohm scale resistors, we're going to see effectively no current flowing into or out of our input terminals. And so that's where this is coming from. Now, I want to be really clear here. I have made no condition on the current that can flow into or out of the output terminal of the op amp, right? So there's only a restriction on the current that can flow into or out of the input terminals. Whatever current needs to flow out of the op amp's output terminal can. Now, I mean, I say that like it's definitely possible to pass too much current and burn it out, but from a circuit analysis standpoint, whatever we need to come out of it can come out of it. I'm sorry, what? So we are not looking at the whole picture here, right? So we're just looking at the op amp itself, not as part of a greater circuit where there will be conduction paths and stuff like that. The second rule for an ideal op amp is there can be no potential difference between the input terminals of an ideal op amp. This is what's known as the op amp voltage constraint. And effectively what this means is that the voltage at the non-inverting input terminal must be equal to the voltage present at the inverting input terminal for a negative feedback ideal op amp circuit. Another way to think about that would be to say that the voltage drop between these two nodes is always zero. I'm sorry, what was that? What did, oh, the three, so must be equal to. All right, so we have established our two rules specific to the analysis of ideal negative feedback op amp circuits. And so now let's take some time and analyze some circuits. And so what I am going to do here is we are literally going to work homework set number 16. These problems legitimately are, I'm about to come off like a real asshole here, so easy that they wouldn't have taken you more than 15 minutes to do from the jump. So we're not really, it's not as nice as you think it is, but it does provide useful practice. There's my stylus.
Yeah.
All right, so here is our first problem that we are going to be looking at. Let me draw it back on my PDF thing really quickly. So this is homework 16.1. And in this particular problem, we have some source current, let's call it 4 milliamps. Here is our op amp. I'm going to explicitly ground my non-inverting input terminal here. And I'm going to put a resistor here. Let's make it 2 kilo ohms for the sake of argument. And then I'm going to measure my output voltage here. Okay. Let me make sure that this is consistent with the WebWork problem, and then we're going to break some things as it were. Yep, this is consistent. Okay. So a couple of things here. I'm going to identify some nodes. Sorry, this should be a V minus because it's here. So this voltage V minus that I've drawn here is the voltage present at the inverting input terminal measured with respect to ground. So this is a nodal voltage because it is measured with respect to ground. Similarly, the voltage here, V plus, is the voltage at the non-inverting input terminal, and it is also a nodal voltage because it is measured with respect to ground. All of the voltages that we're going to deal with in an op-amp circuit are going to be nodal voltages, okay? So I'm going to give you guys what I believe to be a fairly simple process for solving these circuits, okay? I want us to apply rule number 1. So that's step 1. So we are going to observe that these currents must be 0 amps, okay? We are then going to determine V plus. So I'm looking for a number here. What is the voltage present at the non-inverting input terminal of our op amp? 0, because it's shorted directly to ground. Step 3 is to apply rule number 2. So if this voltage is 0 volts, this voltage must also be 0 volts. Step number 4 will be to apply KCL at the inverting input node. So I'm going to be adding this current plus this current together and setting them equal to 0. So my current flowing to the left, we can see by inspection, is -4 milliamps. My current flowing up through the 2 kilo ohm resistor is 0 volts minus V out divided by 2 kilo ohms. And I set this equal to 0. because I know that no current can branch off and flow to the right into the input terminal of my op amp. And then lastly, I will solve for V out. So solve for V out either using the numerical solver on your calculator or the 2 algebraic steps necessary to make this give you a number. The numerical solver on the TI calculator and also on the Casio calculators uses an iterative solving process based on what your initial guess value is. And so the closer your guess is to what the actual value is, the faster it will solve. I usually just put in 0 or 1 and just let it go to town. Yeah, so it's doing the calculation over and over and over again, trying to get closer and closer until it settles to some specific value. I don't know. I just know how the numerical solver works. I never looked into how the system solver works because I had a similar question of why is it taking 3 minutes to do something so easy? All right, what number did you get? -8 volts. All right. This simple process with maybe a potential modification to step number 4, because there might be more than one node we need to do KCL at, is literally all you will need to analyze any op amp circuit in this class. That's it. Okay. There are some tips and tricks and stuff that we're going to look at on Friday, covering the different types of circuits, or really it's to illustrate how to set up a circuit to perform specific mathematical operations. That will be what Friday is about. But with regards to circuit analysis, we're kind of done. All right, so let me show you what I mean. Let's work homework 16, number 2. So in 16, problem 2, it's the exact same circuit, but we now have, oh, actually, yeah, well, that'll be fine. The same exact circuit, but we now have a voltage source connected to our non-inverting input terminal. So here's our current source. So let's make this 2 milliamps. Let's make this 4 volts. Let's make this 5 kilo ohms. And here is our output voltage. All right, so what's step 1? So applying rule number 1, we observe that this current is 0 amps and this current is 0 amps. What's rule 2? Or sorry, what's step 2? My apologies. All right, so V plus is the voltage present at the non-inverting input terminal. What will it be in this circuit by inspection? 4 volts. Now we will apply rule number 2, which tells us that the voltage present at the inverting input terminal is equal to 4 volts. Now we are going to apply Kirchhoff's current law at our inverting input node. So that's going to look like -2 milliamps plus 4 volts minus V out divided by 5 kiloohms is equal to 0. And now solve for V out. Yep, that's it. All right, so for those of you that took the time to solve this thing for V out, did you get the same result of -6 volts that I got from doing the math in my head? Yes, okay, great. So I want to identify a couple of different red herrings that you may see on homework problems, exam problems, etc. Okay. So what if I had included some resistor here, which I'm just going to label R plus. Its value isn't particularly important. If you saw a resistor placed between the voltage source and the non-inverting input terminal, would that make any difference whatsoever in your circuit analysis? Correct. So it will not make a difference because the current flowing through that resistor is 0, which means there is no voltage drop over that resistor, which means it is doing literally nothing. It's behaving as if it were a short circuit because there's no current flowing through it, right? So having a resistor value in that position literally does not change our analysis procedure in any way, shape, or form. What if I had included some load resistor, RL, across my output terminals? So I was trying to deliver power to some load, maybe a small speaker or something like that using this amplifier circuit. Would the presence of this resistor RL in any way, shape, or form impact our circuit analysis? Absolutely not. Okay. Only if RL happened to have a value of 0 ohms, meaning that we were directly shorting our output to ground, would it have any bearing on our analysis whatsoever. Okay. So there are lots of little things that can be thrown in there to trip you up that represent things that you would do in a practical circuit. But from an analysis perspective, particularly dealing with an ideal op amp, they're actually not going to have any impact whatsoever. All right. Any questions about this one before we move on to the next one? Where would it show up in our analysis steps? That's why it doesn't impact our analysis. It literally will not show up in the 5-step process that we've developed. All right, let's look at problem number 3. So this one's a little different. So let's put my op amp here. If my memory serves me correctly, I have some DC voltage source here. Let's call it 2 volts for the sake of argument. I have some DC voltage source here. Let's make this 5 volts. Five kilo ohm resistor. $10 kilo ohm resistor. Here is our quantity V out. So I want to say something here really quickly. there is no practical reason why you would ever put a battery in your feedback loop for an op-amp circuit. There's literally no practical reason why you would ever do it. It is going to impact our analysis very slightly, but not bad. Okay. All right. So what's our first step going to look like? Apply rule number 1. 0 amps flows into our input terminals. Okay. Second step. V plus will be equal to 2 volts. Third step. V minus will be equal to 2 volts. Now we are going to apply Kirchhoff's current law at our node, right? So in this case, that's just saying this current is equal to 0, okay? So things are looking a little awkward here. But let's think about this in context. If that current is equal to 0 amps, what must the voltage drop across that 5 kilo ohm resistor be? What was it? 0. So the voltage drop across this 5 kilo ohm resistor must be 0 volts. So what do you guys think V out will be now? So it won't be 2, nor will it be 0. We have 2 volts, and then we have 5 volts of the opposite polarity. So what should V out be? Effectively, what we're doing is we are doing Kirchhoff's voltage law from here to here, recognizing that the voltage drop across the 10 kilo ohm resistor is nothing more than our nodal voltage V out, right? So we'd have negative 2 volts plus 5 volts is equal to V out. Excuse me, plus V out, so equal to negative V out, my apologies. So V out should be negative 3 volts. The only reason we had to change our analysis method is because of that asinine battery in our feedback loop, which I cannot iterate enough would never be an actual thing. Okay. Oh, June. When doing Kirchhoff's voltage law around that loop, we would have negative 2 volts plus 5 volts plus V out is equal to 0. Moving V out to the opposite side will give us that negative sign. I just missed it when I was doing it in my head. So to be clear, V out is a nodal voltage measured with respect to ground, like every other voltage in an op-amp circuit would be. So the positive polarity terminal of V out would be at the output node of the op-amp. The negative polarity terminal would be at ground, which is why we have these signs. Does that make sense? All right. Any further questions about this one? Look at problem number 4. This is one of my favorite ones. So we have our op-amp like so. Our non-inverting input terminal is grounded. We tie our inverting input to our output using some resistor. Let's call this 7 kiloohms just for the sake of argument. We have some, let's say 3 milliamp source here. And our goal is to find our voltage at our output pin with respect to ground. So what's step one? 0 amps here, 0 amps here. Step two. Step three. Step four. This current, which we know will be 0 amps. What's V out? 0 volts. Yeah. So a really fantastic question that has been asked multiple times is, well, where the heck does that 3 milliamps of current go? That 3 milliamps of current winds up flowing into the output node of the op amp and then gets dissipated to ground through one of the power supply rails in a practical system, but the power supply rails never show up in our actual analysis, which is why I stopped drawing them. Okay. So we are not creating or destroying any current here or charge or anything here. It's just we don't see the mechanism by which it's getting dissipated because it's not part of the analysis process. Let's look at number 5. Well, number 5 is the same thing as problem 3, except slightly easier because the resistor isn't there. So V out should be V2 minus V1. All right, this one, this particular circuit, which I believe is also pretty much exactly what your in-class assignment problem 1 looks like, is more akin to the type of circuits that you should expect to see on your exams and also on homework number 17, actually. Okay, so let's take a look at this guy. So I believe we have some voltage here. Let's call it 3 volts. Let's make this 5 kiloohms, 8 kiloohms. Ten kiloohms. Ground this guy right here. 17 kiloohms here. Trying to find V out. What's step number 1? I want you guys to be bored of this at this point because it's literally the same thing over and over and over again. I cannot impart on you enough how this process will work for literally everything I'm going to throw at you. 0 amps here and here. What's the next step? V plus is 0 volts. What's the next step? V minus is 0 volts. What's the next step? Write our KVL equation, excuse me, KCL equation, right? So this current plus this current plus this current have to equal to 0. So that's going to look like 0 minus 3 volts divided by 5 kiloohms plus 0 volts minus 0 volts over 8 kilo ohms. So the 8 kilo ohm resistor is effectively shorted out. Plus 0 volts minus V out over 10 kilo ohms is equal to 0. Just for the sake of argument, we can throw that away. And so we have negative 3 volts over 5 kilo ohms is equal to V out over 10 kilo ohms. V out is equal to negative 3 volts times 10K over 5K is equal to negative 6 volts. Or throw it in your numerical sum. All right. Just to prove that I am not being facetious with you, I'm going to open up one of the practice exam 3s. Oh, no. Full test. Exam 3. Let's look at this one. Randomly picking one. I believe this was one when they were still cumulative, so I'm going to have to scroll a bit to get to the op-amp problem. Let's see how irritated I was with the students of fall 2019. Pretty irritated. So we have this hot mess of a circuit, and I'm about to illustrate to you that literally the easy peasy process that we've been dealing with is perfectly capable of handling this nightmare of a circuit. So what is our first step? Zero current flowing here or here. What's our next step? All right, so we need to find V plus. Now for this particular circuit, this is actually going to take, I would argue, some effort. Not a whole heck of a lot by any stretch of the imagination, but some amount of effort. Can anybody think of how we might go about solving for this voltage V plus? It is not 6.1 volts. Troy. Okay, so what Walker has suggested is that the voltage drop over this resistor is 1.2 milliamps, and I need to give myself a little bit more room, times 4.1 kilo ohms with this particular polarity. He is correct. Knowing that piece of information, how do we solve for V plus? Because it isn't just going to be that current times that resistance. (6.1 plus). They're of the same polarity, right? Okay, so V plus 11.02 volts. Okay. So 6.1 plus 4.1K times 0.012. Okay. Again, just to be really, really explicit, V plus is a nodal voltage. So what we were looking for in this case was effectively the voltage drop over the current source. Because we can't find the voltage drop over the current source directly, we had to do KVL around that little path. I don't know if you guys were aware that that's what you're doing, but that was exactly what you were doing in those steps. Okay. So applying the fundamentals, always great. All right, what do we do now? V minus is going to be literally the exact same voltage. So now we apply Kirchhoff's current law at the inverting input node. So that will be this current plus this current plus this current. So what's that KCL equation going to look like? Well, I'm gonna be lazy because I would have had V minus stored in my calculator. Sorry, so that would look like V minus negative 3.9 volts divided by 4.7 kilo ohms plus V minus divided by 5.3 kilo ohms plus V minus minus V out divided by 3.7 kilo ohms plus 9.2 kilo ohms is equal to 0. And then I would solve for V out. Yep. Yep. And I'm just lumping them together as if it were a single equivalent resistance. Yep. The 8.9 kilo ohms does not impact anything. So just as like our process here worked, there's a slightly different way that we could do this. I'm trying to think. I'm trying to think if I want to show you guys using Thevenin equivalent circuits to make this look like a form that we've seen, which isn't necessarily required, but it's a useful application of Thevenin equivalent circuits. Yeah, and to be clear, this material is not on the upcoming exam. Yeah, no op amps on the test on Monday. So for this particular problem, let me show you what I mean here. Finding the Thevenin voltage of the system will actually make this part right here a little easier to figure out what V plus was, right? So if we were to disconnect this network, let me draw it over here. I mean, it's realistically just doing the steps that you guys just did, 4.1 kilo ohms, 1.2 milliamps, and then tying these together and finding this VTH. You would find that VTH, sorry, this was 6.1 volts, would wind up being 11.02 volts, and RTH would just be 4.1 kilo ohms. And so you would put your VTH here, and you could see from the jump then that V plus would have to be VTH, right? It's just a simple analysis tool. So if you're ever given something at the input side of your circuit that you're like, what, I'm not sure how to find what my voltage V plus is, you can always take the Thevenin equivalent circuit of that network to find V plus. That's all I'm trying to illustrate here. I might have done it poorly, but you'll see a few circuits to where it might make sense to use the Thevenin equivalent voltage as opposed to doing all kinds of weird other tricks. Anyways. All right. So this is the first op amps lecture. We've accidentally, not really accidentally, done the overwhelming majority of your homework set. You could probably knock out that last problem or two that we didn't do in a couple of minutes. In-class assignment. Go nuts.